Okay, so to remove a trend, so that's a persistent trend that's not vanished through transformations, we want to think about removing it either through differencing or by detrending. When we difference a series, we believe that it's initially integrated, so that's a sum of a stationary series with itself at a lag. Or if we believe that there's a trend to it, deterministic trend, we run a regression to remove that deterministic trend dependent on time. It can be quite difficult to tell which of the two to use. When you're in real doubt and it's not obvious that there's a trend, perhaps try using both. We can difference integration away if it's present. One way to tell if integration is present is to see a slow decay. So again, a linear decay in the ACF would suggest that there's integration present. Exponential decay would be suggesting that there's not integration present, and if there's a sharp cutoff, then we've certainly not seen integration. We can also try fitting an AR1 process and see if the coefficient of the AR1 is close to 1, bearing in mind the standard errors on the estimates of the AR1 coefficient. And there are also formal tests that we can do for integration and stationarity called the Dickey-Fuller tests, KPSS tests, and runs tests. If we find that after differencing once, which is justified, the series is still non-stationary, we can try differencing several times. Something to bear in mind though is that you can over-difference a series. But one of the benefits of differencing is that differencing, say, k plus 1 times will remove a polynomial trend of degree k. Okay, so here we fitted an ARIMA to a stationary process, and its AR coefficient is not -1 or 1, so that's fine. We don't expect that to be integrated, and the ARIMA fit suggests that it isn't. If we had something close to -1 or 1, depending on how R reads it, we'd then expect that differencing was justified. Okay, so we'll now perform an augmented Dickey-Fuller test, which will test the null hypothesis that this process is non-stationary. And the output of the test is essentially based around, again, the ARIMA type fit procedure, but made more formal. The output of the test is that the alternative hypothesis of stationarity is valid simply because the probability of watching a statistic as extreme as this under non-stationarity is very unlikely. It's a p-value less than 1%. Let's run a KPSS test. It's just a more robust version of this test. And the KPSS suggests that stationarity is valid. The p-value associated with watching this data, stationarity being the null hypothesis, is around 10%. In fact, it's higher than that if that's what we're being told. We can also run a runs test. And what a runs test does is it checks for the direction of the time series as we look at it at its increments. And if the process were to be truly stationary, then by differencing we shouldn't observe any particular changes taking place. However, when we look at the statistic, we get a very small p-value which suggests that the alternative hypothesis that the process is two-sided, i.e. it goes up or down in either direction without a particular tendency either way, is quite likely. Let's do the same with the example time series. So we'll fit an ARIMA first, and we can see straight away that the AR1 fitted there, it's got a very small standard error, but it is more or less on 1. So we can probably accept that the process is integrated and that it needs differencing. We can look at that differently through an ADF test or a KPSS, so the augmented Dickey-Fuller. That suggests to us that we should take the null hypothesis of non-stationarity as being true simply because we observe a p-value of almost 11% with the augmented Dickey-Fuller test, and with the KPSS, the null hypothesis of the process being stationary should be rejected, and we should accept the alternative, which is of non-stationarity, since we observe a very small p-value. Similar to before, we can run a runs test. By going through the runs test, we accept the alternative hypothesis that the process is two-sided and non-stationary. We can do a similar thing with Barclays closing share price data. Let's try to say that again. Okay, this produces an error because the process has already been identified by the ARIMA fit as non-stationary, it won't estimate the AR process. Let's try the augmented Dickey-Fuller. And again we observe a really high p-value, which suggests that the null hypothesis of non-stationarity is valid. And working with the KPSS test, we observe a very small p-value, which suggests that the alternative hypothesis of non-stationarity is valid for the KPSS. Performing a runs test. Oh, that didn't seem to work. Let's try that again. We just need to process the data before it's sent through to the runs test function. And that is dichotomous, so it is 0. Oh, it's 1, 0, minus 1. The runs test doesn't work so well with zeros. You could deal with that just by randomly shifting a 0 to either a plus or minus 1. We won't do that since we're fairly happy that the process is non-stationary for the Barclays daily closing price. Something that should happen is that if we difference and it's appropriate, then the variance of the difference process should be less than the variance of the original process. Let's see how that works with the stationary process. So remember, the stationary process shouldn't be differenced. And when we do, we find that the difference is actually greater than the original difference variance is greater than the original process variance. So by differencing, we've differenced too much and increased the variance of the process. Not desirable. Whereas when we look at the example time series, differencing has a positive effect. It reduces the variance of the process. And similarly with the example, no, okay, so this here needs to be Barclays daily closing price. Let's get that right. And again, the differenced process, that it has a variance that's less than the variance of the original sample. We can look at that more clearly through a function. I've defined a difference variance function. It just essentially calculates the variance after differencing the data once, twice, up to a default number of 5 times. And let's see what happens. I'll just run that function through first, then do a plot of it. Okay, let's just do that again. That's a function defined. Oh no, it's not. Okay, I'll try that again. Okay, so this is the complete function. Here it is defined. And let's try using that to look at the difference variance for the stationary process. Okay, that's just linearly increasing, so we shouldn't difference the stationary process at all. The example time series, which shows that the variance is minimized once it's differenced twice. And the Barclays closing price, we see the variance there is minimized once it's differenced twice too. We should just note there